Hi everyone, this is, like it says, types of radiation detection. It should be a review, but if you haven't done it yet, it needs to be done. All the resources that accompany this were sent out on Frog previously, but from the objectives we're trying to hit with this session is to describe how a Geiger-Müller tube works. That's one of the detectors used for nuclear radiation. Describe what alpha, beta and gamma radiation are and comparing their ionizing effect and penetrating power. And also recalling the relative masses and relative electric charges of protons, neutrons, electrons and positrons, which are new, and list the 5 types of radiation that we need to know about at GCSE. Nuclear radiation comes from an unstable nucleus. The clue's in the name, it's nuclear radiation, it comes from the nucleus. And we mustn't ever forget that one. And anything that emits the electromagnetic radiation by a random change of their nucleus are called radioactive. That should say random, not random. So it's a random process where the nucleus changes and electromagnetic radiation or particles is given out. As the animation, there's your unstable nucleus, and it can either give out waves of electromagnetic radiation or some sort of particles, as we shall learn in the rest of this activity. Detecting radiation is one of our first things we need to be aware of. How is it detected? Well, it can't be seen, it doesn't smell of anything, it doesn't make any sound. However, we can detect its radiation. And in the early days, and in fact how it was discovered, was in the days of photographic film. When radiation gets near it, it affects the chemicals on that photographic film, and when you develop the film, it can actually show that. And that was how radioactivity was discovered. Here's an enlargement of that sort of first photographic plate, and the story is that French scientist Henri Becquerel was given some rock to test that was claimed to have great properties, and he couldn't do anything chemically with it, and he put it in his drawer and forgot about it. But in the next drawer down was some photographic film, and he wasn't aware of the connection until he wondered some months later what was on the film, developed the film, and saw this sort of pattern as you can see there on this film, and wasn't able to explain it. But being a scientist, instead of just throwing it away, he actually thought, well, why might this have happened? What's above it? And thought, there's that mystery rock I was given, and went back and repeated the experiment and discovered that this mystery rock caused the sort of alteration of photographic film. So in the early days, before electricity and stuff was really taken off, photographic film was used to detect nuclear radiation. However, today we have more technical devices, and the one we need to know about is the Geiger-Müller tube. And this can be used in many ways to detect and measure radiation, but the Geiger-Müller tube is actually the detector part of this setup here. You've got a radioactive source of some description, you've got the detector, which is the Geiger-Müller tube, and you can attach it to various devices, whether it counts it in terms of total number of counts, or rate meters, counts per second, and various other measuring devices. But the Geiger-Müller tube is our key thing. Hollywood films love to call it a Geiger counter, but its proper scientific name is Geiger and Müller. Okay, so we need to know a bit about that one. 1 becquerel, named after the fellow who discovered it. The unit of nuclear decay per second, the number of clicks on a Geiger-Müller tube, is 1 becquerel, BQ, capital B lowercase q. And that's the unit that you measure that activity. How many decays per second are happening is measured in becquerels. But we need to have an idea of how the actual Geiger-Müller tube, this detector, actually works. Basically, it's a cylinder which has got low pressure gas inside it. It's got a very thin window of mica usually, which is like a type of a very thin glass that nuclear radiation can pass through. And the outside of this cylinder is a negative potential, and the centre of it is at a very high voltage positive. Now obviously in normal times the gas in it is an insulator, so no electric charge can flow. And as you can see in the diagrams below, we can see that the gas particles in there's the central positive electrode and the negative outer case, and that's how it is normally. Nothing's happening inside there. However, if some form of nuclear radiation enters this Geiger-Müller tube, as is shown by this wiggly arrow here, what it can do is it causes ionization. These are ionizing radiations, which we'll talk about in a minute. And that ionizing radiation will ionize the gas particles, the gas molecules or atoms. And as they're ionized, one is positive and one is negative, and they will move towards the positive or negative side of this tube. and in doing so actually create a flow of electricity, which is then detected on the counter, the electronic part of the device. But that's how a Geiger-Müller tube works in terms of what goes on there. Now, one of the activities that I set you previously was to match up the statements for this. So you should have done that, what's connected to what. And if you haven't, do that before I put the answers up on the next slide. You might want to pause the video, find the activity and do it, and then when you've done it, return to the next slide, because what's coming next is the answer. And it matches up like that. You shan't go through it all verbally, but you can pause the video and check your answers to see if they're correct. But those are the statements that describe how the Geiger-Müller tube actually functions. Okay, so that's the Geiger-Müller tube, how it works. There's videos about that. You can research a bit more about that and follow it. But we need to know the basics of that and be able to discuss the statements as you should have done. Okay, and then moving on to the next two learning objectives, which we need to cover. Okay, so we've talked about the unstable nucleus. I like this animation, so we'll do that again. And it can either emit an electromagnetic wave or a particular type of particle, of which there are 4 we need to know about and appreciate. Okay, the randomness, which I've changed the spelling of, is important, and if they do that, they are radioactive. And it's the emissions that we're really interested in the ability to knock out one of these electrons. Okay, and these are the very basic ionizing radiations that we need to know about: alpha, beta, and gamma. And if you look at the images that represent these, hopefully, you know, as intelligent young people, you can actually already start thinking, okay, I know what that symbols mean. I can guess what the others are, and that may mean something similar. And we've studied these in some detail in a previous module. So alpha, beta, and gamma fit into those, and we need to know a bit more about each of those and a couple more. Okay. Adding to that, we also need to know, well, we know electrons, but positrons are probably new to us. We've never come across positrons. Chemistry don't understand them, but we need to know about a positron. And effectively, it's a positive electron. Okay, mind-blowing concepts, but that's what a positron is. It's like an electron, but it's got a positive charge instead of negative. And neutrons should have come across before, but neutrons can also be thrown out of unstable nuclei as well. So all these particles, aspects of nuclear radiation that we need to
what you see here are the 3 types of radiation streaming towards you.
Photons, gamma rays, we've studied
gamma
rays,
photons. In the middle is the helium nucleus, the alpha particle, 2 protons, 2 neutrons. And on the left-hand side is the beta particle, the very fast electron. You'll notice that the gamma rays and the beta particles are almost travelling at the same speed. That's because the beta particle is travelling at a speed quite close to the speed of light. If I bring a piece of paper in, what you'll notice is the alpha particles are now unable to penetrate through. The gamma rays and the beta particles, though, can still get through. If I bring a piece of aluminium in, that's enough to absorb the beta particles, and they are no longer getting through, and there's no significant reduction in the number of gamma rays. If I bring in a large piece of lead, that is enough to absorb a significant number of the gamma rays, and the count rate drops right down.
Down the centre of those. Now, I provided this table for you last time, and this link to this great website, Andy Darville's website, which has got all the data on, all the information. Very good it is for nuclear physics and other elements of physics. And we need to have a sort of understanding of the properties of these particles. So that needs to be done at some stage. And at the end of this session, I'll sort of put up the information that you need to know on that. But that's an independent task for you, and that's a summary table. And you need to know about these. Its symbol, what do we show it as, what's its structure, what's it made of, what's its relative atomic mass, does it have a charge, penetration power, what can it pass through and what stops it, and what ionizing effect does it have, how effective is it as at knocking electrons off other atoms. This is something that really visualizes nuclear radiation. This is a cloud chamber, okay, and basically what this does, each of these little wisps of what looks like smoke represents the sort of an alpha particle being thrown off this central source here. And if you think when aeroplanes fly across the sky, they have the vapor trails behind them. This works very similarly. It's a sealed device with a low pressure vapor in, and as the alpha particle is thrown out, it causes ionization, and the vapor forms a trail on those ions. So say you see planes fly across the sky, and these are sort of doing the same sort of thing. They're having a track of how far alpha particles go. And as you can see, they're not going very far, a few centimeters, and we'll return to that. But cloud chambers, we can actually visualize and see the path that these tiny nuclear particles okay, again, this was in the previous activities, but we need to be able to align these and match the statements of alpha, beta, positrons. Notice beta minus, beta particles, we get the sort of Greek capital B, beta, with a negative, because a positron is actually, because it's an electron but positive, is given the same beta but with a plus. Gamma is, again, the Greek letter gamma. It's like an inverted, it's like a capital Y, and neutrons, as you should know from chemistry, are that. So we need to be able to match that up, and if you haven't done it yet, make sure you do, because these following, pause the video if you haven't, are how it matches up. Alpha is helium nuclei with 2 protons, 2 neutrons. Beta minus is a high energy, high speed electron. You should know the details about it there. Positrons are high energy particles with the same mass as an electron but positive. Gamma rays, we know that from electromagnetics work. And then neutrons, we should know what those are. So we need to be confident in doing that. Penetrating power tells us what things will pass through. And as you can see, gamma will go through everything, even thick lead. It'll only reduce by thick lead. The beta particle is going through the paper quite happily, but it's stopped by thin aluminium, stamped on Coke can. And alpha particles, big and heavy lumps that they are, moving slowly, struggle to get through your skin, fortunately, or paper. So in terms of what penetrating power these have, we need to have an understanding of that. What stops them? Paper for alpha, aluminum as the Americans would have it, for beta, and gamma will pass through all of those, and the thick lead only reduces it. It doesn't stop it, it actually only reduces it. So it's pretty hard to completely stop gamma, and we need to be aware of that one. Thinking about the penetrating power and the range of these, alpha particles are pretty big and heavy, as you can see here. 2 protons, 2 neutrons, quite big really. So if that's trying to pass through the air, it's going to bump into the air molecules and be sort of interrupted and stopped quite quickly. So in air, alpha can only pass through, between 2 and 4 centimeters of air before the standard gas particles in air stop it. Beta, being a tiny, high energy, fast moving electron though, can wiggle through all the air particles. So the range of beta in air is, tens of centimeters, 20, 30, 40, 50 centimeters in air before those are sort of like stopped by bumping into the air molecules and atoms. But gamma, as you can see, gamma can quite happily pass through air because it's not bothered about aluminium or paper, and only lead reduces it. So gamma has a range of meters in air in terms of its range it can pass through. This table summarizes those. Okay, alpha, because it's such a big heavy lump of a particle, is very good at ionizing things. It's a big heavy lump. If you don't hit something with a big bowling ball of a particle, it's going to do some damage and knock off electrons quite easily. So alpha has very good ionizing properties there. So they don't go very far, but they're very strongly ionizing. Beta particles, being smaller, if an alpha particle is a bowling ball, then a beta particle is about the size of a pea. They're much less ionizing because they're much smaller, but they can go further into things because they're small and high energy for that one. So they're less ionizing. And gamma rays are much less ionizing because they're energy waves, but they penetrate things very easily. So we need to be aware of those properties too. To summarize them, then alpha particles, 2 protons, 2 neutrons. It's a helium nucleus if you think about the periodic table. 2 protons, atomic number of 2 is helium, plus 2 neutrons gives it a mass number of 4. And that would be helium, but we don't have electrons orbiting it, we're just about nucleus, because these are coming from the nucleus. So it's a helium nucleus. Electric charge +2, it's got +2 protons, no electrons, mass of 4, penetrating power centimeters, paper, strongly ionizing, it's a big heavy lump. And an magnetic field, because it's charged, it will be deflected. The electric charge is affected by magnetic fields, and therefore it will actually move by a magnetic field, but because it's big and heavy, it doesn't move far. Beta radiation, beta minus, again it's a high energy electron, electric charge of -1, a mass of nearly 2,000th of an atomic particle. Penetrating power, a few millimeters of aluminium or a few meters of air, tens of centimeters. Ionizing is weakly, and it's strongly deflected. It's got a charge, but it's very light, so therefore it's bent in terms of its direction. It's attracted very strongly or repelled by electrical and magnetic fields. Gamma rays, as we should know about these from our other work, no charge, no mass. It's a wave of energy. Several centimeters of lead. It's not really stopped. It should be reduced. Concrete's good, but again reduces it. It's weakly ionizing, but it is dangerous from that point of view, and it's not deflected. It's got no charge, so it's not deflected. Okay, that's a summary. It's a bit of a whistle-stop summary, really, of the particles you need to know about and their properties. So we need to know those. And I sent out with the frog work some work on some past paper questions that kind of address this area of knowledge. So either you've done them, great, well done, let's see how you did, or you need to do them before we go through the answers. But these are the questions that I've sent out, and you need to be able to, use your knowledge to address these. This is from March 2013, Higher, which is the older GCSE, but the physics hasn't changed since that one. So we've got questions about alpha, beta, gamma radiation. State two ways in that gamma is different from alpha. And complete a sentence, A, B, C, D. A beta particle is emitted by, again, be careful with the language on there. Part 3, complete the sentence. A beta particle has the same charge to A. And then explain how an atom becomes ionized by radiation for 2 marks. And this is an interesting one because this is an unusual context to test your knowledge in, really. It's an old camera with a removable lens. You can unscrew these lenses, still can on digital cameras, but you can remove the lens, and it's got various bits of glass in it. One of the pieces of glass is radioactive. Surface is covered with a thin layer of magnesium fluoride. So it's the glass that's radioactive, and it's got a coating over that of magnesium fluoride. Radioactive isotopes, which you should have done, in the glass emit alpha, beta and gamma. So all 3 of our main sorts of radiation are given out in all directions. And the scientists take the lens off the camera. She measures the radiation coming out the back, out the front, and out the sides of the lens. And the amount of radiation is different. Okay, so this is the radioactive thing with alpha, beta and gamma, but we get 3 different rates of activity in the different directions, and we need to say why that is. Okay, so again, pause the video and do the questions if you haven't, but if you have done them and you just want to know what the answers are and go through it with me, we'll go through answers and explanations. 2 ways in which the gamma radiation is different from alpha radiation. Okay, gamma is a wave. Okay, alpha is a helium nucleus. Alpha is charged. Gamma isn't. Alpha has a mass. Gamma doesn't. Gamma penetrates further, but alpha doesn't, or properties of those. Gamma is weakly ionizing. Alpha is strongly ionizing. Gamma travels faster, speed of light, etc., and the opposites apply. So for 2 marks, you should have been able to get those. Pause the vid if you want to have a look at those and write them down and check your answers. Secondly, complete the sentence, etc. It's D. A beta particle is emitted by an unstable nucleus. That's the fundamental random process in an unstable nucleus gives out radiation, and it's a beta particle in this case. A beta particle has the same charge as an electron, B. A beta particle is like an electron, small, fast-moving, high-energy electron, but coming from the nucleus. There's a contrast, really, a bit of a conflict. Electrons in chemistry in an orbit, but this is an electron coming out of the nucleus, which might get you scratching your head, and we'll talk about that next lesson. So answer beta there. Explain how an atom becomes ionized by radiation for 2 marks. Okay, electrons are lost or gained. Okay, that's the fundamentals about what ionizing is. Okay, radiation causes electrons to be, and we're really interested in lost here. Radiation causes electrons to be lost. You could use less scientific language, knocked, removed or released, but let's try and get it right in the first place. It's not positive electrons, because we know that electrons are negative. So electrons are lost would be, there we go. It's a big thick cylinder of aluminium here. This is all beta and gamma with, I would say, quite a lot of alpha. Just gamma, just gamma. I think that's, quite a useful question, really. Might have had you scratching your head about it, but it's an unusual way of testing your knowledge on those things. Hope it was useful. Another exam style question for this one. Compare and contrast the emission of an electron during the ionization of an atom with the emission of an electron during beta minus decay. Okay, so ionization, chemical idea, chemistry idea, whereas beta minus decay is different. So for 4 marks, what would you put about the compare and contrast? How are they similar? How are they different? Okay, if you haven't done it, pause this, write something down, because I'm going to reveal the answers on the next slide. Okay, there we go. So, an atom becomes ionized when it absorbs energy. Yep. When electrons leave the orbit. Remember, ionizing works for chemistry and physics. You ionize something by removing an electron, or adding, from its shells of electrons. So that's the ionizing part. It needs energy to do that, as we've seen about promoting energy, electron energy levels. If we give it energy, it will go to an outer level, and if we give it enough energy, it'll go right out of all the energy levels, all the shells, and leave the atom and ionizing it. However, beta decay is nuclear radiation. Nuclear means it's from the nucleus. Okay, so that one's from the outer electron shell being removed, and one is being emitted from the nucleus. Again, it's a bit of a sort of conflicting thing. You've studied for years that electrons are in orbit, but now we're saying in physics that beta decay is an electron from the nucleus, and we'll come to that next lesson. And it's a random process of unstable isotopes. So there we have, fundamentally, 4-point answer to this question. Know the difference between ionization and beta minus decay. And finally, in the plenary for this one, most of the time, true or false. Again, if you haven't done this, then pause this and decide true or false for these. And the answers are as follows. Most of the time we're not exposed to ionizing radiation at all. Well, we are. Okay, it's false, that is, because background radiation, as you should know, is around us. It's radiation, it's ionizing. It's not very strong, it's not dangerous, but it is ionizing. Background radiation is not ionizing radiation. Yes, it is. So that's a false statement. Generating electricity using nuclear fission produces highly reactive waste material. We'll come to that in the future, but that is true. It does produce waste material. That's one of the problems with it. A lot of benefits to nuclear power, but there are drawbacks too. Radioactive waste can be chemically processed to make it harmless. No, it can't. It can be reduced in its activity. It can be put in containers that reduce what the radiation can escape, but it's still not harmless by any means. People with X-ray equipment, that's radiation, isn't it, from electromagnetic work, need to keep their exposure to a minimum. Yes, they do. X-rays are still ionizing radiation. Some radioisotopes decay into radioactive gases. Yes, they do. Radon gas, background radiation, is important that we know about. People are exposed to ionizing radiation. They have an increased risk of developing cancer. Sadly, they do. True, because the ionizing effect of it affects the genetic material in cells and can cause mutation and uncontrolled cell division, which is what cancerous growths are. The best defense against ionizing radiation is to stay as far away as possible from it. Yes, it is. Yes, gammas can pass through those, but basically, the further away you stay away from it, the better it'll be. And when we ever do practical on this, that's what we shall see. Okay, so I hope that's been a useful summary for you. You can rewind it, revisit it, have another look at it, have a think again. You can email me if you want to ask any questions you're not sure about. But I hope that was useful. So more to follow. Thanks.